Alright, so I'm here to tell you about soft lithography. And if there's any main takeaway message that I hope that you all take away from this, it's a really quick, inexpensive, versatile way to make micro and nanostructures. And the beauty of soft lithography is that it's very accessible. So in virtually any lab, you could use these ideas. And we're going to do some of this in our lab. Hopefully you'll be able to go from here and do some of this in your own lab. If you need to, you can come and use our lab later on if we have something you don't have. But the main takeaway is it's sort of the quick and dirty microfabrication way. So the outline for what I'll be telling you about, I'll kind of give you rationale, why bother with this, what are some definitions. I'll also tell you about the main materials that are used. So it's based on elastomeric or elastic polymer stamps, basically just rubber or silicone stamps. PDMS will come up a lot. It's the most common material people use for soft lithography for historical reasons, but also for a lot of actual, there's a lot of really cool properties of PDMS. We'll get into that. PDMS actually stands for polydimethylsiloxane. It's a mouthful, so I won't say that very much, but PDMS. Then I'll tell you about two of the main techniques, or two of the main processes people use, where they take soft lithography and apply it to their own application. So there's replica molding, where if you're making microfluidic channels, you're just making copies of something. Replica molding is the way you go. And then during David's presentation, he also mentioned, and Lena also mentioned this, microcontact printing, where you print some sort of ink, where you sort of stamp something, you can get down to nanometer features. So microcontact printing is also the other option. There's a lot of applications. There's no way I could possibly cover all of them, but I hope that you'll get a sense of what the main ones are. Alright, so soft lithography, the long, boring definition, actually it's not that boring, but the Whitesides group, I think, from the 90s, we're talking 20 years now, but they had a recent protocol review, and if you're interested in basic, how do I do this, what are the common processes, this is a good paper to start from. Because they actually list all their steps and all the little tricks that they do. And when things don't work, they actually have it in red where be mindful of this may not actually work. But the main idea is printing, molding, embossing with an elastomeric stamp. It's fairly simple, as you'll see. And we'll put the slides out on the website too, so if you're looking for reference, don't worry about copying them really quickly. Alright, so I guess as a bit of context, you've all heard about conventional lithography. Leno talked about this. You've seen some of this in Kate and David's talk as well. We can get really accurate planar structures. I really like thinking about the cell phone idea, right? Because if you think about how fast the computers were when they first sent people to the moon, and how fast our computers are now, or how fast our smartphones are. Conventional lithography, photolithography is great. You can get lots of cool things with it. The rationale for doing soft lithography is, if you're in an academic lab, for example, and you want to test something really quickly, you have some application you want to try out, and you want to be able to do this fairly quickly. If you don't necessarily have regular access to a clean room, or if you don't have a very expensive machine, or if you just want to test something really quickly, just a quick and dirty, can we do this? I think someone mentioned they were doing paper-based microfluidics, and that's a really cool example of rapid prototyping where you can test something really quickly in a day. So soft lithography kind of fits this mindset where you want to do a very, very quick test of something. And the beauty of it also, though, is that you can do powerful things too. You can do really meaningful scientific experiments with this. So, I've kind of covered most of this. Lots of applications. You can do non-planar structures. You can do curved structures. You can use different kinds of substrates. You can print cells. You can print proteins. I probably shouldn't get ahead of myself, but we'll get there. So, elastomeric stamps. Why PDMS? Why did we start with PDMS? PDMS is a family of silicone rubber polymers. It's really squishy and stretchy. I should pass some around so that you actually see it. The features on these are actually, some of the same ones that you'll be using in the lab sessions. You'll get detailed explanations of what's actually on them. But for now, just look at them. They kind of look cool and they're bendy. If you hold them up to the light, you may be able to see the features better because it is transparent. I've got lots of them. Some of them are devices that we make in our lab for grant and the project that we're working on for bacteria detection. There's no bacteria on them; these are just PDMS pieces. But feel free to pass them around. While that's going around, I'll just continue. So it's made up of these siloxane backbones, and you've got this soft and rubbery feel to it, where it's really squishy. If you look up PDMS and places where it's used. I'm trying to think of this, maybe all of us have used PDMS in some form today. So do people actually know where you might find PDMS other than in these like squishy rubber things, like other places where PDMS might be? It's not called, like, I guess people don't really advertise it, but one place you can find PDMS is as an anti-foaming agent in chicken with nuggets. I would not advocate eating your PDMS pieces, but they do use it there. It's also in shampoos, as it makes your hair slippery and shiny. What else is it in? Lubricating oils, breast implants, or back in the day, and lots of different places. So PDMS is ubiquitous. People really like it. From us, you've seen the slide already, how we make a PDMS mold. You pour the liquid pre-polymer and curing agent onto a master. And so you saw this in Lino's talk as well. The idea is you do go into the clean room if you have like really fine features, and you can make your wafer, and then you pour PDMS onto it, and I'll pass this around as well. And this is actually one of the wafers that you'll be using in the course later on, so you'll see that a lot later. So PDMS itself, when you make this rubber, you have a base, a pre-polymer, and you have a curing agent. You mix them together in a ratio. The ratio determines the properties of your PDMS. Usually you mix them together in a 10-to-1 ratio to get that same feel and consistency that you use. We cure it. The temperature and time of curing varies depending on what you're looking for. But you can cure it at 80 degrees for 2.5 hours. It's a thermal curing process. It's relatively slow compared to, say, injection molding, where you get things in seconds. You peel off the stamp, and you trim the edges, you punch some holes, and that's it. You've got your elastomeric polymer. I guess I'm throwing some terminology around. When I say master, I just mean the original wafer that has the opposite of the features that you want. So when I mean stamp, I mean your PDMS. You'll do this in this workshop. All right, so for us microfluidics people, we like PDMS because you get this conformal contact. The conformal contact is a really, really big thing with PDMS. If you have one device where you have channels and you're trying to seal it against a flat substrate so that your liquid doesn't leak out, then conformal contact here means that you get really, really good sealing, even if there's imperfections on the surface. Also, if you're trying to print features onto a substrate, it's really nice if you get really, really good contact. So conformal contact is really good for PDMS. You also saw this, where you can do a plasma oxidation, and you can turn PDMS that's normally hydrophobic into hydrophilic. This is nice because if you're trying to move blood or proteins or water or buffer through your channel, it would suck if you just put it there and it just stays there because PDMS is hydrophobic. So a quick plasma oxidation makes it hydrophilic. And just looking down here kind of illustrates what's going on. You have your siloxane groups, but the plasma oxidation gives you these hydroxyl groups on the surface, and that's what makes it hydrophilic. The purple tint, and you'll see this in the lab as well, just comes from having ionized gases in the plasma, and as they relax back to their regular states, they give off photons, and it looks really cool. It's a blue glow. Wish I could carry plasmas everywhere, but that might not be safe. Another thing that's cool about actually doing plasma oxidation with PDMS, it's a really simple way of bonding two pieces of PDMS together, and you get a pretty good seal. So you just plasma oxidizer, you get these reactive groups, you seal it against the flat piece of PDMS, and you've got channels that don't leak. So it's pretty useful that way. What else do we like about PDMS? So there's a lot of them. The fact that you have a liquid pre-polymer means you can pour it easily. What else? It's transparent, so if you're doing some sort of experiment where you need to monitor what's going on, it's pretty nice for that. Pretty good chemical stability. Alright. So I don't just talk about all the good things about PDMS. I suppose I should mention some of the downsides a little bit. One thing David mentioned earlier was that if you're doing a commercial process, right? If you're thinking about making CDs and you're making a lot of them every second, if you're talking about PDMS and you have to do slow thermal cure for a couple of hours, that's kind of a big deal. In a research lab, we're not making CDs yet, right? Like, I don't know if any of us is making 1,000 devices a day, but if you're trying to go from a prototype to a commercial product, PDMS might not necessarily be what you want. Then some solvents will swallow PDMS, so that you start to get your devices looking weird. That's not necessarily nice. I also wanted to point out that other than PDMS, which is the traditional workhorse of this field, there's other materials too, and they have different appeals for why people use them. So one of them is this Asti, osteochrometric. Another mouthful, naturally, but osteochrometric silane polymer. And the appeal of using Asti is that with these, you can pour the liquid polymer onto your master and UV cure it in a matter of seconds. So you can do this in maybe 10 seconds. It also has some really neat features because based on the composition of the polymer that you're using, you can get either really soft and bendy or really stiff, like a thermoplastic. So there's a lot of research going on here. The other thing that this is illustrating too with Asti is because you can have these excess diol groups on the surface, and then you can easily functionalize the surface. So Kate mentioned one of the really common biological assays people like to do in microfluidics is immunoassays. And there you have an antibody binding to some antigen. And if you want to immobilize an antibody in the surface, something like Asti makes it fairly straightforward for you to immobilize some sort of capture group on your surface. I have a more detailed slide about Astis here, just to show what they're useful for. And you can have a bottom layer and a top layer where you have excess diols on your bottom layer, excess alleles on your top layer. And then by the time, when you bring both of them together and UV cure, then you get really, really good bonding between your two layers. So it also gives you advantages in terms of bonding. Don't worry about all the details with this. If you're interested in them, the slides are online. You can tell you more about it too. But it's just to give you an idea that PDMS is just one of the materials that you can use. So we've got an elastomeric stamp that we just passed around. What do we actually do with this? What are the processes we do in soft lithography? So replica molding is one of the big ones. You've just made your stamp. Well, just use it as a template, right? You go into the clean room, you make your wafer, you get your stamp. Using that stamp, you can make multiple copies of something else that you can peel off of the PDMS. Usually, you'll probably want to maybe silanize the surface or coat the surface with something to prevent it from sticking to whatever you're making copies of. But yeah, you can peel off copies. Since the 90s, people actually showed you could make more than 50 replicas from the same stamp. So it's sort of a quick way so you don't have to go into the clean room so often. And this just comes down to like preschool Play-Doh kind of replication. The neat thing about it, though, is that even with these replicas, you don't get that much shrinkage. It's only about a 1% difference. Of course, you'll have to do tricks to get such good reproduction, but it's pretty nice. You can use a different material, say polyurethane, for your replicas. So this is from 1998. I was looking at other stuff we could talk about that's more exciting about replica molding. But before I get there, though, I wanted to mention there are some limits, right? You can't just replicate anything and get out of PDMS and it'll be perfect. Life doesn't work that way. There are defects. So with replica molding, one of the things you need to keep in mind is the aspect ratio, or the ratio of your height to the length or of your features here. There are practical limits here. So if you've got a device here where you've got a very high aspect ratio, there's this tendency for your features to start to collapse. If you've got them spaced out too much, then you've got this tendency for them to sag. And this is something that I've actually run into in the lab, where I was trying to replicate really high aspect ratio features, and there were defects everywhere. So if you're trying to make something out of PDMS, be mindful of it. There's ways to get around it. You could also use a different material, but there are limits in replica molding PDMS. So I was looking at other cool stuff you could do with replica molding with PDMS, and there's this paper in Science in 2000, and what they did was they had a multi-layer soft lithography where you have PDMS on a master, a thin layer, and then you have a thicker layer, and you just bond them together. Here, the bonding was actually accomplished by having excess functional groups within the PDMS. So on the thin layer, they had an excess of vinyl groups, and on the thicker layer, they had silicon hydride. And so by the time they ended up curing them, you got really, really good sealing without necessarily having to do your plasma treatment technique. And the advantage of this is, if you have, so you can stack the layers like that and have multiple different layers. What they used this for initially was pneumatic pumping of liquids. So you can have liquid moving here, and these cross channels, the top layer, you can have air going in. So if you have air going in, you can push on the channel to close the channel, or you can not have air going in, or have a vacuum, have it open, and then the liquid can flow through. So now you're getting sort of a measure of sophisticated liquid control. It gets better because, like now, starting from the simple cross channels, we're talking you can have several layers of features, say 3 layers, I think, in here. And so you have a control layer where you have a liquid flowing through, it presses down on the flow layer and it closes the valve. I know these look complicated, but what they actually end up doing with them is really, really cool. And I'll show you a video to sort of illustrate this. So, once I start going with the video, a lot of things start happening. But the main idea is they made fluidic logic circuits where they were trying to make liquid circuits analogous to electrical circuits, where you have a bit passed into it and it moves from step to step to step. I'm an electrical engineer, so I'm kind of biased and I like this stuff. But even if you're not into electrical engineering, you can think that if you can have an automated system where you can have really, really good control over where your liquid goes. If you're trying to do an amino acid, if you're trying to do a PCR reaction where you need to mix that liquid with that liquid, it gives you a lot of flexibility. Anyway, I'll just upload this video of a microfluidic shift register where you have some control lines at the top, and you have these lines on the bottom where you get different outputs showing up. It's only about 40 seconds long, but it's pretty cool. Wish there was some music to go with it. But yeah, it's just passing a bit through based on the input that you put up there. And again, this is just to illustrate that starting with something really simple, just putting a layer of PDMS on your surface, stacking them into layers, by arranging them and by creatively thinking about how you want your device to work, you can get these different layers. I should mention that you need to plug this into an air and a vacuum pump, so you'll have some external control lines for this. But it's pretty neat. Is it still going? Ah, it's done. I don't actually know what the code that they put in is. A series of zeros and ones. But alright, so I've talked about Replica Mode in a bit. Now I want to shift gears a little bit and talk about microcontact printing, where you have your stamp, and you're inking your stamp with different things and making different features on your surface. Which is the official definition of microcontact printing here. So we're going to go at this one from the historical route. How it started initially, or some of the first materials that were microcontact printed, were self-assembled monolayers. So the idea was you have your PDMS, you put a solution of alkane thiols, which will form your self-assembled monolayer. They diffuse into the stamp, and now your stamp that contains the ink, you press it onto a metal substrate, and then you've transferred your self-assembled monolayer, and then you use this as a mask for wet etching, like Lino mentioned, and then basically you get your patterned substrate. I guess to think about this in context, why this was appealing was when people were doing this initially, if you wanted to pattern a metal, you needed to go through all these processes, perhaps go into a clean room, define your features, and then pattern it this way. If you could do this in a lab where you have a PDMS stamp, and you could do the rest of the processes in your lab, where you could just put some self-assembled monolayer on there, do a wet etch in your lab, then it's a pretty quick way to pattern metals. So it's kind of cool in that sense. I'm going to tell you a bit more about the self-assembled monolayers. There's a lot of chemists in the room, and if I say something wrong about self-assembled monolayers, feel free to jump in. They're pretty cool. You've got a covalent bond between your thiol group and your coinage metal, and then you get this organization into this close pack structure because there's van der Waals interactions between the tails of your alkane thiols. Like everything in real life, there's imperfections, but using these self-assembled monolayers, you can still use them as a mask, and you can have self-assembled monolayers in the areas you don't want to get etched, and in the exposed areas your metal gets etched. It can get these fancy patterns out of like nickel or gold to make microelectronic structures. The self-assembled monolayers are only about 3 nanometers thick, so you can't really use them as a mask for reactive ion etching or some more, like Lino was mentioned, where you have ions actually bombarding the surface, but it is pretty cool. So, what else can you print with microcontact printing? You can print proteins. The way printing proteins works is very similar. You have your protein solution, diffuse it into the stamp, you press it onto your substrate, you take it off the surface, and you've got your pattern. The reason why the proteins will bind to the surface is because of surface energies. So your proteins will go from a low energy surface onto a high energy surface. So your stamp, which is hydrophobic, the low energy surface, and your substrate, which is high energy because maybe you've plasma treated to make it hydrophilic. When you press your stamp there, the proteins will move from the low energy surface to the high energy surface. You get pretty good protein transfer. I think it's interesting to think about this in terms of why would you bother to print proteins? So some of the work that's going on in the lab by Sebastian at the back, what we're looking at doing is we print adhesive proteins that we know that neurons like to grow. And then what we do is we do co-cultures of supporting cells, astrocytes, and neurons. And then we look at how the neurons and astrocytes grow together in these adhesive substrates, adhesive proteins. The cool thing about this is you could use it as an in vitro model without needing an animal model to study how different chemicals affect neurons and the supporting cells. So, this platform could be a way to study pretty meaningful physiological processes in a lab by using some reference and protein. Yes?
In the slide before, there's a blow dry step.
Yes.
That doesn't denature the protein?
No, it's a pretty quick blow dry. It's like 30 seconds.
So at what temperature?
This is at room temp. So it's just, we do this, I think it's like less than 30 seconds, just so that your ink doesn't spread, and it just gets rid of excess. The other thing I wanted to show, also from our lab, is we've developed a lift-off technique for microcontact printing to get down to about 100 nanometer protein spots. And the goal here is to see, as you increase the density of these spots, how do the cells respond to these patterns of proteins? And the idea here, and it's also similar to that gradient generator idea, is that inside your body, there's different gradients of proteins, different concentrations of proteins. And your cells will respond to these concentration gradients. So the idea is to see how neurons and astrocytes will respond to these concentration gradients. And the applications here could be if you're looking at how your nervous system gets modeled. Or if somebody has a spinal cord injury, and you're trying to see how the neurons regrow or move towards these protein cues, then having something like this in a lab setting is a pretty neat way to explore that without needing an animal model. I've got more. There's a ton of things you can print, but just a few more to show you. Somebody mentioned bacteria, I think, and ecology. I have a slide for you. So I think you've probably seen this already because you mentioned this, but the idea of a bacteria printing press where you have an agar stamp, similar idea, you put your cells in the stamp, and then you have a medium where the cells can grow, and then you print your bacteria. And you can get all these different fancy shapes, say bacteria printing press with actual bacteria. And the cool thing about this, though, is you can print different kinds of bacteria onto the same substrate in different patterns and see how the different kinds of bacteria interact with one another. So that's pretty cool because all of us have, I don't want to say a mess of bacteria, but like a bunch of bacteria inside our systems. And looking at how those interact could be pretty useful for some biological conditions. I think something like C. difficile, where people actually get bacteria transplants from other people into them to see if that actually helps improve their condition. So being able to do this in a lab is a useful way to test that. And then for the engineers and for the electrical engineers, I wanted to throw something out there as well. Flexible electronics. So the idea here is you can have nanomembranes of conductive materials. So you could have, say, silicon, and then have a flexible substrate, say polyamide, and do a microcontact print onto your flexible substrate, and then get circuits built out of that. Why would you want flexible substrate or flexible electronics? If you're trying to interface with biological systems that are not planar, we're all not robots with transformer shapes. If you want to get really good contact, for example, with someone's brain, if you have a mesh electrode, the conformal contact of PDMS would come in again here, or of an elastomer would come in, so that you can get really, really good contact, get high-quality measurements. Here, I think we're seeing an electrode being put into a cat brain near the visual cortex. And then the images here, they injected something called I always forget the name, picrotoxin. It causes a very strong stimulant response. Apparently, it's a banned substance in horse racing. But you see really weird patterns in your visual cortex if picrotoxin is injected. And with this electrode arrays, they could record what was going on when they injected this. So to finish up, I just wanted to say, we'll be looking at some soft lithography microcontact printing in this course. We have patterns of stripes. I don't know if you saw those in the mask that I passed around, but there'll be some stripes. Part of the purpose of the stripes, we have a variable pitch here so that you can see how well the patterns are transferred, and as they get wider, do you get some sort of sagging or some collapse? Where do you start to get defects? That's kind of the main gist of all of this. I'm hoping that you got the sense that there's a lot you can do with this. It's rapid, inexpensive, pretty accessible. There's a lot of applications. You can find a lot of papers of soft lithography. I hope that you will all find it useful in your own research. And if you have questions, I'd be happy to answer them. Just want to thank the DJ group for their feedback on this. Yeah. Thanks. Yes?
What is the highest resolution you can get in the soft lithography?
That is a good question. Off the top of my head, I don't actually have a number. Like, we're still talking in microns here, right? We're talking, like, if you're making replicas.
So you had 15 micrometers for the parallel stripes that you showed in the previous slide.
Yeah.
You can get 15.
Yeah. Yeah.
But you don't know about the nanometers.
Yeah, no, it starts to get tricky there.
And is there any physical limitation about the capillary phenomenon?
Oh, like,
for the just highest resolution, how deep you can go?
so if I'm understanding correctly, you're asking like for capillary-driven like flow of liquids, like what channel?
Yeah, how much thin they can go for the.
So that's a good question. So how capillary forces scale with the depth of your channel? If you have a rectangular channel, then some of the things you want to keep in mind, like Kate mentioned, you've got a pressure at the interface between your liquid and the air. It's sort of the wicking pressure that's pulling the liquid. And so that pressure, it's proportional to 1 over the height of your channel. So if you've got a small channel, then you've got, or the smaller you make your channel in that sense, then the more pressure you have pulling it. But you've also got a flow resistance. So the smaller you make your channel, actually you've got a resistance to flow. So if you've got a rectangular channel, then you've got, actually the flow resistance scales as like your height of your channel to the power of 3. So now you've got this, so in terms of physical limitations, generally you basically want to balance the pressure pulling your liquid and the resistance stopping your liquid from moving. So it gets better as you move to smaller scales, but yeah. Yes?
How many times can you make PDMS replicas on SU8 master?
On a single SU8 master?
Yeah.
That's a good question. You have to be gentle with it. I think in our lab, once we get the SU8 masters from the fab, we silanize them so that we don't get much sticking. But once you've made your first PDMS replica, then you can usually make a bunch of them. I think right now we keep ours for a year, at least until we see some sort of wear and tear on them. So I don't actually have an exact time for you, but we can use them for a lot of replicas. I don't know. Sebastian, do you want to comment on this?
They start degrading after about a year, but it depends how frequently you use them.
Yeah.
So for the nano patterns, we started noticing after 40 replicas.
Yeah.